Good afternoon, everybody. Ladies and gentlemen, this session we continue focused to the media distribution, but more specifically about the things more technical, protocols, as streaming, objects distribution, but also economic aspects. Mr. Macri this morning was showing us with figures the profound change in the media distribution, moving mostly from broadcasting to on-demand online. And this technological change is challenging, some aspects of which our new speakers will discover. I present you first time at Edward Smith. Edward is retired from British Telecom in May 2016, but remains involved as a research fellow with his main research areas being network modeling, telecommunication history, and the development of the new ICT telecommunication proposition. He partners with researchers in the UK and Italy on a range of projects. He is a regular contributor to ITP and FITCE publications. He is also a fellow of the British Computer Society, member of the Institute of Telecommunications of the ITP, and is UK board member for FITCE, and Chartered Information Technology Practitioner, a Chartered Engineer, ICB accredited consultant, and a TOGAF accredited enterprise architect. Ed, you have the floor.
As this says, I'm here to introduce you to QUIC, which is Quick UDP Internet Connections, a layer 4 transport protocol brought to us by Google. That was handy. I'll be taking you through basically how we build up from the presentation layer down to the transport layer. And really what you'll see is how these payloads influence the viewing experience, why we need QUIC, how it affects, how it impacts performance, and we'll take a look at its performance. So this is Cisco's view of the world as far as IP goes. First of all, the bulk of traffic is consumer traffic, so that's people accessing the internet. That's where the majority of video streaming is coming, which you'll see is the green line. You might be also interested in the red line, which I've produced a couple of pie inserts there, that show you that mobile traffic is increasing from about 10% in 2016 to 21% in 2021. So very much as previous speakers have said. So we're looking very much at how do we assess the user's quality of experience. So it starts off with a couple of very simple, fairly brutal ones. First of all, is the video that I wish to see available? And secondly, please, it's not so appalling that I choose to give up. Assuming that both of those are okay, we take a look at the lower level performance issues. So the first one is when I press the start button on my video, how long is it before I see anything happen? Following that, we have the idea of rebuffering. So the network has to deliver data to the to the client, which is going to do the playout. If it doesn't present it quickly enough, then your video stalls. And direct measures of quality are how often does that happen? When it does happen, how long do you have to wait for the network to catch up with the display? And finally, what quality are you getting? Now, quality, as we've seen already from Lawrence, and this summarizes, hopefully, whoops, wrong direction, some work. As we increase quality, we increase the number of bits being sent, also how frequently they're sent, and we get some pretty horrendous bandwidths, again, as Lawrence showed us. But with compression, we can bring them down to a manageable level. And compression is probably the next place to talk about, because this builds up on the OSI stack, the presentation layer. What happens is chunks of video is assembled into small chunks, manageable chunks, and the first frame in any chunk is taken as an anchor. And all subsequent frames are built from that anchor as changes. That greatly reduces the amount of data that is sent. Now, in a streaming service, the way you handle that is you produce several different encryptions, several different encodings to different levels. So I've shown here red, blue, and green. So we take green as low quality, the red as medium, and the blue as high quality. Typically, the server will implement this capability known as adaptive bitrate. And the first thing it does is it asks the server for data at a nominated bitrate. And it then asks the question, am I receiving data quickly enough to allow me to display a full buffer? That full buffer will allow me to, sorry, can people hear me? Yes, okay, good. That full buffer that full buffer allows you to avoid rebuffering. Oops. Sorry. So if the network isn't delivering quickly enough, the client will notice and will request low quality video, which sends less data, giving it a better chance to keep up. This is adaptive bitrate. If, however, it also finds that it's could receive data quicker and therefore up the quality, then it will ask for that. So where does that fit in with the OSI stack? Well, at the very top, it fits in at the presentation layer with HTML5, which is the latest version of HTML. This has two features: better video support and also the capability of interfacing with ABR software. Now below that runs HTTP2, which we saw this morning. HTTP2's the latest variant, which was developed from a Google protocol known as Speedy, and its key feature is it allows you to multiplex multiple video streams across a single TCP session. The other key thing is increasingly we're seeing video encrypted. So we have, again at the presentation layer, this thing called TLS, which confusingly is called Transport Layer Security, and that sits alongside HTTP2. So looking at below this level at the transport level itself, how the two interact, we'll see that the video server will supply across the network video frames. These will be variable length, and these will be received by the native TCP software of the operating system, which operates at system level. You'll see why I make that distinction later. That is read by the playout application that reads into the playout buffer. Now, normally you would dimension that buffer to ensure that it never overflowed. But in fact, TCP is going to look after that, because TCP error recovery and congestion control will stop it overflowing. However, what you are interested in is the probability that it will ever become empty. And the speed with which that empties is driven by the quality of video you've requested. So you've got what is effectively known as a GD1 queue. So we've covered quite a lot of technology there, and the reason we've covered it is because 3 of those layers we've talked about in some detail will disappear into QUIC. So QUIC operates at application space. That means it's less efficient than processes operating in systems space, and it's the yellow bits that change. So we have the bulk of HTTP2's capability, all of TLS2, and the congestion control and error recovery of TCP are all pulled into QUIC with a null transport layer in the form of UDP. So QUIC was invented by Google in about 2012. It's a relatively low part of the internet traffic, so between 2.5% and 9%. These are 2017 figures, but it's increasing. So it's got a number of design goals. First of all, that it is deployable in user space. The reason for that is Google want to develop this on the fly. So there is no guarantee that the version of QUIC running today is the same as ran yesterday, and it's very unlikely that you will know about the difference. It's got a more sophisticated way of multiplexing streams, and it improves loss recovery. Loss recovery is one of the great strengths of TCP. It's one of the areas where TCP adds overhead, and it's one of the things that slows you down as well as protects you. They also wanted to make sure that no one could do anything in the network that that would actually slow down rollout and slow down development. So what it does is it actually encrypts an awful lot of the payload and hash protects the control headers and protects from snooping eyes both control packets and data packets. And it also, because it uses UDP, your firewall is less tolerant of UDP than it isn't than it is TCP. So when you run a NAT session, it will be less stable. And what QUIC has to do is use a connection identifier to protect your mapping of IP addresses in that NAT session when it re-establishes it, which it will do transparently. This basically makes the point that TCP and HTTP together imposed a large number of limitations. So first of all, HTTP would only have a one-to-one correspondence between HTTP sessions and TCP sessions. There are ways around it, but they have their limitations. The big problem you have, what you're trying to do is stop a single data loss event impacting all of your transactions across your network. That got better with Speedy and HTTP2. Speedy, of course, Google spelling, which allowed you, first of all, to multiplex multiple TCP sessions, multiple HTTP sessions on a single TCP session. And what Quick does is it actually allows streams to recover independently of each other. So if you hit an error on a quick stream, then everything on that stream doesn't stop. Only the streams associated with the errant packet are actually impacted. So there are a number of performance gains. You saw we collapsed a number of layers. One of the reasons for doing that is each of those layers had a series of handshakes associated with it when you set up the session. What QUIC allows you to do is merge those sessions into a single interaction. Also, it allows you to cache information across sessions so that in the event that you cancel a session and then want to restart it, you can do it with minimal exchange of information, which speeds up session establishment. It's removed head-of-line blocking and put in a number of mechanisms to greatly improve transmission error handling. One of the key ones there is avoiding the the confusion between, am I not getting an updated response because I've lost data in transit or because there's an error? And the latter is much quicker and easier to recover from. So it's important to know the difference. Otherwise you're back on worst case. They did try a thing called forward error correction, by which you send a redundant block of information down, and rather than going to error recovery across the link, you could reconstruct that block. Unfortunately, the extra data that you sent more than impacted the amount of time you recovered. So they've dropped that. Much better congestion control, and the item that I'll draw your attention to is the last bullet point. There are two processes in TCP flow management. One is at the very start, which is called slow start, which you avoid going down to. The other one is congestion avoidance, which is where you try and stay. There are a number of algorithms or approaches around for managing congestion avoidance, some more efficient than others. And the one that they've initially tried with Quick is a thing called Cubic, which is available in Linux. And what that does is, in congestion avoidance, it handles error recovery fairly aggressively, not based on how quickly you get responses back, but on it opens up the congestion window with time. Trouble is, there are two alternatives, one of which Google favours, which is a thing called the, if I can remember it correctly, bottleneck bandwidth and recovery protocol, which is very aggressive. And the other one is a more laid back and traditional one called New Reno, which the IETF, who are standardising QUIC, are interested in. So that's how it's implemented. What does it look like in practice? Well, there are two approaches to testing. One is taken by Google, who have a luxury that no one else has. Since most of the interactions use their servers and their browsers, they can put hooks in there and gather huge amounts of data from the live internet about how this protocol performs. And then obviously know what the current version is. And they can look at aggregates and get wonderful information about how it's performing. There is a problem with that, in that when you take that approach, you can't vary things a parameter at a time. So if you've got something slowing you down, you can't tell what it is. Now, Google have also made available Quick software through an open source program known as Chromium. That allows individual researchers to build browsers and servers themselves and test in the lab. The good thing is the two methods of testing are broadly in agreement. And We see there that generally for search latency, we see that Quick is about 8% faster. Video latency, so that's when we're waiting after pressing play for our video to catch up, is again an 8% improvement. It's worth having. Video rebuffering is 18%. But those are average figures. If you're in South Korea, where the network is excellent, those figures will be nice round figures of 0. If you're in India, where it's not so good, you'll get much bigger improvement. Now, as well as this, there are a few other little things independent researchers have discovered and publicised. There are some, in particularly engineered harsh environments, that they've managed to identify. There are others that, well, the main one is that they find that Quick is very unfair to other protocols, which is something that they don't really acknowledge. And it was also independent researchers that noticed that forward error correction didn't work too well. So how widely is it used? Well, basically, the number of endpoints is increasing rapidly. Most of them are on Google's network. A fair number are on Akamai's network. Akamai are a big CDN provider. In terms of traffic, it's nearly all on Google, and we're seeing more traffic on mobile ISPs than on terrestrial ones. That may well be down to the predominance of Google's involvement in Android. So briefly going through security. Security is intrinsic. Work has been done by a number of researchers who've discovered that this is very efficient. It works as it says, but it does open some new attack vectors. A couple of side effects. First of all, because everything's encrypted, it's very hard to look inside of the packets. So if you're using other forms of network security or managing the network, then that's very difficult. The other thing is it is not yet up to the standard of TLS 1.3, which it needs to be for PCI transactions. And so to conclude, IP is a given. Quick does have some merits, but they're not always obvious. It's been in IETF draft state since 2012. That's a long time, but not unusual. Some design decisions are yet to be finalised. So all of those measurements I showed you did not use the IETF's preferred congestion avoidance mechanism. Encryption and authentication give with one hand, take from others. One of the key things I discovered was that it's been looked at for the 5G packet core. So on pure technology grounds, perhaps its selection isn't obvious, but with 5G packet core looking at it and Google behind it, it's something you wouldn't bet against. Thank you very much.